Hi guys, it's Ms. Griffin. We're looking at Unit 8, Skill 5, where we are going back to those T-chart proofs or the because proofs, looking at proving a particular quadrilateral. So no longer with coordinates, but just with a given and a proof. So here's your essential question. How can we prove a particular quadrilateral using given information? So in this first section, we're looking at given a quadrilateral. Step 1 is to first prove that the shape is a parallelogram. That's most often the thing you have to do first, because if you remember, our quadrilateral turns into a parallelogram, and then that parallelogram can turn into a rectangle or a rhombus, which then can turn into a square. So that parallelogram can turn into any of the following shapes as soon as we know that it is in fact a parallelogram. And we can prove that it's a parallelogram by doing one of these four options. Typically the first, I would say, first three are your major ones, but the fourth one also comes up too. So first you want to show that both pairs of opposite sides are parallel. Show that both pairs of opposite sides are congruent. Or you could also show that only one pair of opposite sides is both congruent and parallel. So for that to happen, that would be like looking at this side and this side, both congruent and parallel makes it a parallelogram. Or the diagonals bisect each other. Once it's proven that it's a parallelogram, then we're going to move on to step 2, using the properties of the needed shape, such as rhombus, rectangle, or square, in order to prove. Sometimes you have to prove the triangle's congruent first, use CP/CTC, and then show that it's one of these things. Also, sometimes step 1 is already done because they might give you a parallelogram, but it doesn't always happen. So we've got this first example, and I think your paper actually says something slightly different from mine. It should say AEDF here, quadrilateral ADEF. That's the huge quadrilateral that we have right here. Okay, so we've got this big given. We're going to mark it up in that quadrilateral. AE is congruent to DF, so that's this big piece is congruent to this big piece, and I'll put one hash mark on each. Check it off once I use it. AF is congruent to DE. Here, two hash marks, check it off. Angle F is 90 degrees, so I'll put the box in there. And angle FBA right here is congruent to ECD right here. So again, as soon as we mark it on our picture, we got to check it off, show that we've already used it. So now our goal is to prove that ACDB is a parallelogram. So I'm going to highlight that in yellow and actually shade it in on my picture, so that I know where my focus needs to be. So in order to prove that it's a parallelogram, we have to be able to prove one of these four options from above. Prove that both sets of opposite sides are parallel, prove that both sets of opposite sides are congruent, or one pair of opposite sides are congruent and parallel. And we're not going to deal with option 4 because there are no diagonals drawn, so we're not going to deal with the fact that they could potentially bisect each other. So you can do this in your T-chart proof with your statements and reasons, or we can do the numbered like because proofs, and I'm going to choose to do that option for today. So the first part is obviously just the given. To save space and time, we're going to just draw an arrow, but of course on a test you need to actually write it out. So secondly, I want to think about the shape that they gave us here, this quadrilateral AEDF. And I'm just going to sketch it off to the side here, AEDF. And if you recall, the given told us these sides were congruent, these sides were congruent, and we had a right angle at F. So immediately, because I know that these opposite sides are congruent and these opposite sides are congruent, we know that it's a parallelogram. Because again, both pairs of opposite sides are congruent. But as soon as we stick this right angle in here, it turns it into a rectangle. So I'm going to choose to say that AEDF is a rectangle. And then we've got our because, and I'm going to say that it's because both pairs of opposite sides are congruent. And in parentheses, I'm just going to write parallelogram because that's what it would turn it into if we just had that fact. And there is one right angle. Okay, so then, now that I know that there's a right angle here, I also know that there's right angles everywhere else on angle A, E, and D. But if I focus for a second on these two little triangles that we have a lot of markings on them. This one we have AAS right off the bat, based on just the given statements. This one we have A and S. So the other A that we're missing is the right angle in the corner at E. So now I can actually say that for my next statement, that angle F is congruent to angle E. And this is because you know in a rectangle or in a parallelogram, opposite angles are congruent, and of course in a rectangle they must be congruent because they're all 90s. So I'm going to say because opposite angles in a rectangle are congruent, and if you want to add on 90-degree angles, that's a-okay. You don't have to add it, it's fine if you don't. And now when I look at this, I now can see that I have AAS on both triangles. And that's going to help me out because then I can maybe get a pair of sides or a pair of angles congruent within the actual parallelogram by using CPCTC. So here I'm going to say that triangle AFB is congruent to triangle DEC, and that's because of AAS. And now that I know that those two triangles are congruent, I probably want to focus on these two pairs of sides. They match up with one another, meaning they correspond, and they're within the parallelogram itself. So I'm going to mention that those two sides are congruent. So we've got AB is congruent to DC if I match the corresponding parts, and that's because of CPCTC. Okay, so I'm going to put my hash marks on them and say red. 1, 2, 3. 1, 2, 3. So I can either try to show that that pair of sides is parallel now, because that would be like option 3 from up above, or I can show that the other pair of sides is congruent. And I think that we could get there, because remember how we have this whole side AE congruent to this whole side FD? Well, when the whole sides are congruent and I take away congruent parts of them, like FB is probably congruent to CE because we just showed those two triangles congruent, and these two parts are corresponding. So if I mention that these two are congruent, then I can use a property to allow us to say that AC is congruent to BD. So let's pause for a second and just redraw those two segments so that maybe you can get a better idea of what I'm saying. We have segment ACE and segment FBD. And again, from the given, we know that this whole piece is congruent to this whole piece. We could say from our triangles being congruent that this piece is congruent to this piece by CPCTC. And so therefore, if these holes are congruent and the little parts are congruent, then the remaining parts must be congruent, meaning AC must be congruent to BD. And here's a numerical example so that maybe you can understand it a little bit better if you're struggling. AE is 10, so therefore FD must be 10 because they were already given as congruent. And if we know that CE is 4 and it's congruent to FB because of CPCTC, then that means that the remaining part, AC, must be 6, right? 10 minus 4 equals 6. Same thing applies over here, 10 minus 4 equals 6. So by subtraction, I'm allowed to say that AC is congruent to DB. But we got to remember to put in that step from CPCTC about FB congruent to EC. And again, because it's from CPCTC, I can just lump it in step 6 anyways. So then, or step 5, sorry. Step 6 says that we want to show now that AC is congruent to DB, and this is because of something called the subtraction property. So I'm going to mark that on my picture, think we're at 4 hash marks now. It could be 5 because I didn't mark FB congruent to CE. So now that I see this parallelogram in yellow with opposite sides congruent, I can now prove that it is in fact a parallelogram. So step 7 is the actual proof statement. A, C, D, B is a parallelogram. And this is because both pairs of opposite sides are congruent. Now, I just want to reiterate again that subtraction property started with a whole piece given and a partial piece given to allow us to subtract in order to get a remaining piece. You could also do the same thing if you were given 2 parts here and here. That would make the whole, and that's called the addition property. So that might be used in a proof on your practice or on the quiz or on a test. Flip it over and we'll see another example. Alright, so in this one they tell us that we have a parallelogram given as ABCD, so that's this big piece here. ABCD is a parallelogram, so we might be able to use those properties. And they tell us that BE is perpendicular to CED, so remember that perpendicular lines give you those right angles. And DF is perpendicular to FB, or BFC, and CE is congruent to CF. I'm going to just put check marks on each of those because I just marked them. Now there is something I still have to talk about because I marked this, so I'm going to say state in proof. A lot of you guys mark up perpendicular, but then you forget about it in your proof, so don't forget about it. Blank because given. And again, for the sake of time and space, we're just going to draw an arrow. On a test, you actually have to write it out. So if we want to prove overall that A, B, C, D is a rhombus, that means that we want to get adjacent sides congruent. Need adjacent sides congruent. And I think the easiest way to do this is to deal with the sides that are adjacent within those triangles that you see that are formed here. So we're going to deal with the right angles that are within the actual triangles. So let me get rid of our parallelogram picture so we can actually redraw the triangles. Okay, so the first triangle I see is here. And we've got the right angle at E. This is C and B. Then the next triangle I see is here with C. F is where the right angle is, and D. Okay, so let's talk about those specific right angles, the one here and here. Angle BEC is congruent to angle DFC, and that's because perpendicular lines make congruent right angles. Alright, so far we've got the right angles. I forgot to mark that those 2 parts were congruent from the given. And now we need to think about what else we can get in this picture. I know that it might be like a common thought to just say that BC is already congruent to DC, but we can't say that. That's what we're trying to get to show that it's a rhombus. Take a look at your letters, though. We've got BCE and DCF. Notice that angle C in both of these is in the same position, and the entire angle is in both triangles. So that would actually allow us to say that angle C is congruent to angle C. And recall that whenever you say something's congruent to itself, it's because of something called the reflexive property. So now when I look at my pictures, I am seeing ASA, right, already marked up. So we're going to say that those 2 triangles are congruent. Triangle BEC is congruent to triangle DFC, and that's because of ASA, angle side angle. And then remember, we're trying to show that it's a rhombus, so we're going to show that those adjacent sides are congruent, which happen to be the hypotenuses of both of the right triangles. Therefore, they're corresponding. So we're going to say that BC is congruent to DC, and that's because of corresponding parts of congruent triangles are congruent, CPCTC. And then step 6, because those sides are now congruent, this parallelogram has adjacent sides congruent, and therefore it must be a rhombus. So ABCD is a rhombus because it's a parallelogram with adjacent. Remember, adjacent means just touching or next to. With adjacent sides congruent. Okay, this was a 6-point question on a Regents exam. You see that it was question 35, I believe. So therefore, that means it was worth 6 points. Flip it over. We got one more example for you, I believe. All right, this was another 6-point question on a Regents exam. Again, it's 35 is the question number, and therefore that means it's 6 points because it's pretty much the last question on the test. So we've got parallelogram ANDR with AW and DE bisecting. Bisecting means cut in half. Okay, so if we're cutting in half, sorry, my paper is getting cut off a little bit here. Cut in half. Then we can try to prove that these two triangles, first off, I'm going to highlight them in yellow. ANW and DRE. So we actually have two proof statements here. Prove that the triangles are congruent, and then secondly, prove that the quadrilateral stuck in the middle, which I'm going to highlight in green, is a parallelogram. So sometimes this happens where you have two proof statements and you just take it one step at a time. You prove the first thing first. They put it in a particular order so that you are able to get to the second thing after having proved the first thing. So first we want to prove that these two triangles are congruent. All right, that's like old hat. You've been doing it since Unit 4, no problem. Okay, so we've got this parallelogram. And you want to think about what you know about parallelograms. You, first off, know that opposite sides are congruent, right? So let's state that after we state our given. We're just going to be using any properties of parallelograms that we possibly can in order to get those two yellow triangles congruent. So we're going to say that AN is congruent to match up your parts, DR, because opposites are congruent. And we know that other opposite sides, here and here, are also congruent. AR is congruent to DN. And that's because op sides in a parallelogram are congruent. All right, cool. So far that gives us an S. What else do we know about parallelograms? We know that opposite angles are congruent, right? So that would mean that angle R is congruent to angle N for step 3. And that's because op angles in a parallelogram are congruent. All right, so that's a pair of angles. That's an A. Remember, we need 3 things in order to prove triangles congruent by like SAS, AAS, ASA, so on and so forth. So, Remember that there was this part in the given that said that we were bisecting some segments? We're bisecting NWD, which is this side here, and we're bisecting REA, which is this side here. So that means that each of their parts must also be congruent, correct? 1, 2, 3, 1, 2, 3. Cut it in half. 1, 2, 3, 1, 2, 3. Cut it in half. And the reason I'm allowed to put 3 on these pieces and 3 on these pieces is because those two original opposite sides were congruent initially because of the parallelogram. So we're going to state that all 4 of those parts are congruent right now because I don't know exactly which ones we're going to need later on, so it's easiest just to state them all congruent to each other. So we'll start with RE is congruent to AE, which is congruent to DW, and that's congruent to the last one, NW. And this is because a bisector cuts a segment into equal parts or into halves or something along that line. And technically we're cutting 2 segments into 4 equal parts. So if you want to do that, then we can deal with that too. So now when I look at this, we've got this other pair of sides on here. I'm just not marking it up on the second triangle. I totally could. And that shows us now that we're about to prove our first proof statement. Triangle ANW is congruent to triangle DRE because of SAS. So we got the first proof statement done. I'm going to put a check mark. I'm going to highlight this whole line because it'll show me that I got the first proof statement done before moving on to the second one. Okay, so now the second one says prove that we've got this quadrilateral that is actually in fact a parallelogram. So we so far have one pair of opposite sides congruent. So from here we can either show that they are congruent and parallel or show that the other pair of opposite sides are congruent as well. So it's your choice. Either one will absolutely work. I'm going to go with showing that the other pair of opposite sides are congruent so that you can see using CPCTC again. Because those other pair of opposite sides that I'm talking about are here. I think I'm at 4 hash marks, and here. And they are within our yellow triangles, which means that they are also now congruent to one another because they correspond and they're in congruent triangles. So DE is congruent to AW. And this is because of that 5-letter reason CPCTC, since corresponding parts of congruent triangles are congruent. And so now what we're looking at is this parallelogram with AWDE that has 4 hash marks here, 3 hash marks here, and now we know that it must be a parallelogram because opposite sides are congruent, both pairs. So step 7 will be our last and final proof. AWDE is a parallelogram because both pairs of opposite sides are congruent. And that was our second proof, so I'm going to highlight that in green, and then, well, that's not highlighting very well, it's covering over it. Anyways, I'm highlighting this in green because we know that we just did our second proof, so I can check that off as well. Okay, if you have questions, we know these steps are tricky, these proofs are tricky, please, please, please let us know. Practice before you move on. And I just want to say that your CFU for 8.5 is combined with 8.6. So 8.5 and 8.6 CFU are on the same paper. So you need to get through both videos and practice. Before you move on to the CFU. Okay, so again, 8.5 and 8.6, get through both videos, both practice, and then move on to the CFU. All right, let us again know if you need help. We are here for you. Goodbye.